Um, Thank you very much for joining, for being so brave, joining our workshop in the last slot of CVPR 2017. I've got the honor to be starting our workshop here, which is organized by Dr. Thomas Mensink, currently assistant professor at the University of Amsterdam, myself, Efstratios Gavves, and Zeynep Akata, also assistant professor at the University of Amsterdam, and Dr. Snoek, associate professor at the University of Amsterdam, and also working with Qualcomm in the vision department. So our workshop is going to be about zero-shot learning for computer vision, and we're going to visit a broad spectrum of topics, visit some works that we ourselves, of course, published, but some other famous works from other people, and some explanation first. Many-shot learning, I guess everybody knows. In the standard supervised classification setting, you got a lot of images here, and of course annotations. So that could be a standard case of ImageNet. In ImageNet, you got like 15 million images, let's say, give or take, and then up to a few thousands of labels, or MS Coco for that matter, or many more data sets. Then after you have these data sets, X, Y, you can pass them through any supervised learning model. In this case, we have what looks to be a neural network, a convnet, but it can be practically whatever else. You can have SVMs, you can have handcraft features. That's not really important. Oh, sorry. Yeah. It's not zero here. But the most popular computer vision is the top 5 classification rate in the test set of ImageNet. And then you got AlexNet in 2012 with 16%. And ResNet last year had a dramatic decrease of accuracy, up to 3.6%. And DenseNet now has even been able to beat this number. So many-shot learning is very, very important. So then what is zero-shot learning? Is actually, it constructs to many-shot. So you start from data, X, and then you got a training and test set, and they're disjoint. So the training and the test sets are not the same. So you can actually see a few training labels during training. You can, for example, have annotations for what a car looks like or what a motorbike looks like. But at the test set, at test time, you cannot expect the same type of categories. So you would have images of boats or of parachutes. Now the objective is that given the data X, you would still want to be able to predict what kind of classes you got in the test set, although you've never seen them before at training time. Now a very, very, very legitimate question is why bother, right? Like ImageNet has 15 million images, OpenImages has 9 million images. Places it's 2.5 million images, and datasets are only growing larger. You got more datasets, like I was counting today. On one of the numerous websites that index computer vision datasets, there are, I think, 100 datasets published in the last year. And of course, most of them come with annotations, the labels. So why would we bother? Well, let's give a practical example. let's say we've got this image. This image comes from MS Coco. So in classification, what we would say is that you got a person, you could have a dog and a bicycle, bag, apples, or these are class labels that you can have. This is actually pretty cheap to annotate, right? You can do this practically under 10 seconds. Of course, the obvious problem here is that MS Coco, for instance, has only 80 labels, and there are many, many more object categories that we don't annotate because it's impractical or because they appear very, very infrequently. So that's like one use case, right? So there are a lot of object categories that just are not economical. It is not economical enough to annotate. However, that's not just it. Let's say we're going to segmentation. In segmentation, you have to annotate the precise pixels where the object classes appear in the image. So for instance, you can have the person, the dog, the bags, apples, everything. That's much more time consuming because you have to draw boundaries, you need specific software. Your annotators might not be even agreeing, especially for small objects. So anyways, this actually increases the annotation cost. And then we have also captioning, which has been a very popular task, new task in the last couple of years. So for the same image, like here, you can say that there are two dogs outside looking at each other. That's one way to caption the image, right? Like that's definitely true. You can also say two dogs interacting at an open air produce market. A woman with a dog on a leash walks by a smaller dog, or a couple of dogs greeting each other on a sidewalk. Or you have hundreds of possible sentences. So essentially, for a just single image, there are too many possibilities, which is impractical. It's impractical to expect to have that many annotations. So a nice plot, perhaps, here is the annotation versus complexity graph. When you've got classification, you've got around 20 million, let's say, annotations possible, available, just because it's easier. It's very easy to annotate an image on an image level. Localization, you got around 2.5 million annotations, so you have 2.5 million boxes, let's say. It's an order of magnitude smaller. And image caption, you got like 300,000 annotations. That was like more or less what was the status 6 months ago, at least. And these numbers were computed from ImageNet, OpenImages, and MS Coco. So we see a very nice linear correlation between annotation and complexity. The more complex task is, the more expensive is to get annotation, and therefore the fewer annotations you have. So why zero-shot learning? Because the more complex tasks we target, and that's definitely the case right now, right? Like we're past the point where we just want to say that an image contains a car or a person. We've got less than, I don't know, 2 or 3% error in ImageNet. We're interested in more complex tasks. And the more complex tasks we target on, the fewer annotations we have. And the fewer annotations we have, the more relevant zero-shot learning becomes. So zero-shot learning is essentially something really, really important for having practical computer vision systems. Another reason is privacy-sensitive recognition problems. So zero-shot can actually help you there because you don't need to have a training time, the examples that are required to make inferences. And of course, also, you can use zero-shot learning when learning and inference needs to be efficient. So what this tutorial is about, what we're going to discuss, is about how to do zero-shot learning. So the knowledge transfer, such that we move from the training set of labels to the test set of labels who are disjoint, and how we can learn such an objective. Now, that was a set of introductory slides. Next, we're going to have a very, very, very nice and extensive presentation from an expert in the field, Dr. Zeynep Akata. Then I'm going to give a brief overview of some relevant localization tasks, which I believe are the gist of zero-shot learning. I believe that classification is definitely the source, in a way, how you start about zero-shot, but I strongly believe that localization, being a more complex task, is a very, very relevant direction. Another expert in the field, Dr. Snoek, will discuss retrieval and zero-shot learning. Then we can have a break, and after the break, we're going to discuss about some problems, myself and Zeynep, and in the end, we're going to have a little conclusion. Thank you very much again for coming, and let's have Zeynep.
You can hear me? No? Maybe I hold it like this. Okay. So hello everybody. Thank you for the introduction. I will talk about zero-shot learning for image classification. I'm Zeynep Akata, and I have started as a faculty in University of Amsterdam. Let's start. I will start with motivating the importance of side information, which is really important to be able to do zero-shot learning for image classification in my case. Oh no. Sorry. Well, okay, sorry about that. So I will talk about zero-shot learning for image classification, and I will start with motivating the importance of side information, and then I will present a significant number of zero-shot learning models that are proposed in the recent years that are state-of-the-art for image classification task. And then we presented a poster a couple of days before on unified evaluation of zero-shot learning models, these models that I will present. And then I will summarize with zero-shot learning for image classification at the end. Let's start with motivating the importance of side information. So, like Efstratios mentioned, we have large data sets that are annotated with single labels for images, and this is the source of, for example, deep learning worked very well due to the existence of this kind of data sets. But if we look at the data distribution in these data sets, we realize that some of the classes are very highly populated, such as the cars subset of ImageNet. This is due to the fact that it is easy to collect labels for this kind of classes. Everybody knows what is a car. But ImageNet contains a lot of classes that are fine-grained, and it's not very easy to obtain labels for this kind of classes, simply because we don't see these objects on our daily lives, or we don't know the names of these objects. So in the end, there is the ImageNet dataset, for example, has a very long tailed distribution. In zero-shot learning, we focus ourselves on the tail of this distribution. So we want to solve classification task for the classes for which we don't have enough labeled training data. How can we at all tackle this problem? We make use of side information. So one of the sources of side information that works very well at the moment is attributes. Attributes is a set of properties, usually visual, that we use to associate different classes. For example, in this case, I have chosen zebra and whale classes, and we have example images from these classes, and we have a set of attributes. The next step is to find them or build a representation of these classes. And how do we do that? Some of these attributes are common for every class. So the vector is going to have the same value, or is going to have the value of 1. That attribute is present. Or some of these attributes are specific to one class, so only that class representation will have those attributes as on. And some of these attributes are relative to each other, so we can have values between 0 and 1 also to represent the presence of these attributes for this class. And after building this kind of vectorial representations, the next step is to put this in zero-shot learning framework. So I'm going to present models on how do we do that, but just to have a clear understanding of how we use side information, I'm using this teaser figure. So we embed images in an image feature space, and we build the image feature embedding space. And then we embed classes in the class attribute space, like I described before. And the next step is to find the compatibility between these two spaces. So the zero-shot learning task assumes that we have labeled samples that come from some of the classes, and we have sufficient number of samples. Along with their attributes, but for some of the classes we don't have any visual information, but we have access to their attributes because annotating these is easy. Also, there are different sources of side information that also work quite well, that doesn't require any human supervision. For example, Wikipedia or WordNet. Typically, the classes that we are dealing with are represented as articles in Wikipedia, and we can extract distributed text representations like Word2Vec or GLOV from Wikipedia that creates a structure in the output embedding space. Or we can use hierarchical similarity measures, like for example, in ImageNet, the classes are organized in a hierarchical way. They follow the WordNet hierarchy. And if we want to, for example, define a vector for class 2, we consider the ancestors and the children of this class, or the distance between every node to this class, and build a vector for that class. Just to give some intuition or some examples of how these different side information works, I will show animals with attributes and Caltech UCSD birds results. I chose these data sets because animals with attributes is one of the most widely used data set for zero-shot learning. It contains 50 classes, 40 are used for training and 10 for test, and it comes with binary and continuous attributes. Caltech UCSD birds dataset is a more challenging problem. We have 200 different classes of birds only, so it's fine-grained, and because of that, we need many more attributes. For input embeddings, for the results that I will show, we use Google Net features, and for output embeddings, the class embeddings, we use attributes, Word2Vec, GLOV. Those are extracted from Wikipedia, and hierarchical representation from WordNet. So this table shows that when we don't have any human supervision to build class embeddings, the results are still better than random, much better than random, in fact. So these sources of side information actually contains class discriminative properties. When we combine these different embeddings, which is the fourth line, the results improve significantly, so which shows that these embeddings are complementary to each other. And if we add attributes to this combination, the results improve significantly. So attributes are still much better than any of these unsupervised embeddings, but still these unsupervised embeddings add some information. Yeah. So another source of side information is text. We have collected visual descriptions of objects from people who don't have any knowledge about these classes. So these are very fine-grained objects, and we just ask them to talk about the objects in the scene, not the background or the scene properties. And they gave us very detailed visual descriptions that you see on the screen. The next step is to extract representations from that, and there are several different ways. For example, character level CNNs is one of them. We take every character and we represent it as a binary one-hot vector depending on the position of the letter in the alphabet, and the sentence itself becomes a large matrix of zeros and ones, and we can do convolutions on that. Or we can use LSTMs, again in the character level or word level, which encodes the sequence information in the sentence, which tries to predict the following word given the context. Another way of encoding representation from sentences is combining the two. So we can start with a convolutional neural network that works on the character level. We cut the network from the middle, and then we stack an RNN on top of it. How do these perform compared to attributes, which is the state of the art? So character level CNNs is the black curve. It still doesn't reach the accuracy of attributes, but it is still quite encouraging because this is just convolutions. It's very fast, and the sentences come from novice users. And then if we look at the LSTM, it already performs as well as attributes when we have 4 sentences per image, which is encouraging. Again, this is obtained from novice users. And the hybrid model that starts with a CNN and then continues with an LSTM works much better than LSTM even in the character level. This is quite significant in the birds context. So yeah, even though we may not have access to experienced bird watchers, we can still get discriminative representations from sentences, actually. So another source of side information that we explored is using human gaze. This is motivated by the fact that novice users were able to tell us discriminative properties of objects in terms of sentences. But why not just let them look at the images and they will explore? For example, in this case, we showed two examples that come from 2 different classes of birds to novice users, and we asked them to just learn what are the differences of these images. And then in a second screen, we showed one example of one of these classes, and we asked them which class it belongs to, and they say right or left. And then we collected their gaze information on these images, and these gaze information contains a lot of features like the location of the gaze, or the duration, or the sequence information, which gaze point comes after or before which one, and also pupil diameter encodes concentration level of the user. So these are the type of features that we can get from gaze. The next step is to build per class representations. So after removing the outliers, the gaze points that stay only a couple of milliseconds, one way of building representations is to put an grid overlay on the image and count the number of gaze points that fall on each grid cell and to build a histogram. And then for each class now, we are going to take all the gaze features that belongs to the same class and average that. As simple as that. Another representation is, again, we have a grid overlay, but instead of counting the number of gaze points that fall on each grid cell, we choose the central, the mean gaze point and use the gaze features that I described before, the location, duration, the sequence information, and then we concatenate that for each grid cells. Another one is remove the grid, but choose sequentially, let's say 50 of the first gaze points that fall on the image, and then concatenate that as a representation. And the results show that this is on birds dataset. The representations that encode the sequence information works the best. And we collected gaze from multiple users, and when we concatenate their representations, that also helps, so they are complementary. The gaze is class specific, but people still look at images differently. And then the importance of different gaze features, we found out that the pupil diameter doesn't really help much, but this might be because people get tired after looking at so many images and their concentration level drops. Some numbers, so if we choose random points and do the same as I described, the results are quite low. And there is another work from CVPR 13 that imitated gaze with mouse clicks that didn't have the duration or sequence information, but the location and fewer mouse click points that improved over random bubbles, so random points. And the representations that we extract from Wikipedia improves over that, and attributes are much better than that. But our gaze performs better than attributes. This was surprising for us, actually, and it is also complementary to attributes. But there is still lots of things to be done. This is only on a subset of birds dataset. When we go to large scale, then this method fails. Some visualizations. So the gaze embeddings rank correct images higher than others in these examples. And this was presented as a spotlight in this conference. So as a conclusion, the standard image classification models fail with the lack of labels, and zero-shot learning is a challenging task because of this. We need side information such as attributes, but there are several sources of side information exists. Now I will talk about some, how do we learn from images and using these attributes? What are different models that exist? As a general formulation, we have our sample set is composed of images, X in this case, and their labels. And we have access to only the images that come from a subset of classes. And then at training time, we learn a function that minimizes the empirical risk that has this standard formulation. Here, L is a loss function, and there are different flavors of this, and the sigma is the regularization term. So the F function is a compatibility function, and we are trying to maximize that. And at test time, we assign we take a new image comes, and we project it onto the label space using the W metrics that we have learned. And then we compute the nearest class embedding from the test classes. Again, coming back to the teaser figure, we have images on one side that we embed into an image feature space. We have labels on the other side. We embed it into a class attribute space in this case. And then we learn a compatibility between these two spaces. Here, the X's are given, Y's are given, and the W's is the model that we are learning, the parameters that we are learning. In this, so in the following couple of models, I'm going to assume that we have a linear compatibility function that has this bilinear form. Like I said, theta x's are image features, phi y's are class attributes, and w's are the parameters that we learn. Device is one of the most popular methods that does that, and it uses a convex objective that has a pairwise ranking formulation. Here in the formula, the delta is a 0-1 loss. If the predicted label is correct, then it is going to be 0, otherwise it's 1. And f, again, is a linear compatibility function. If the predicted class is correct, then it's going to be 0, so we don't do any update. Yeah, and it's optimized by SGD. This was proposed in NIPS 2013. And then another flavor of this is putting a weight on the pairwise ranking loss. The rest is the same, actually. And for the weight, as a heuristic, we had used a decreasing weight, so that it gives a high weight to the top of the ranked list than the lower ranks, and it's optimized by SGD. Another flavor is SJE, structured joint embedding. This came out in CVPR 15. And in this case, it's again a ranking framework, but it uses multi-class objective. So we have to, in this case, look at the score against all of the classes and rank it and choose the maximum violating class. This puts full weight at the top of the ranked list, and like I said, it requires computing the score with respect to all the classifiers. So this is slower than the pairwise ranking formulation. And then embarrassingly simple zero-shot learning method uses SJE objective, the multi-class loss, and it adds a regularization term to this objective. Previous models that I showed use explicit regularization. They do early stopping. In this case, there is an explicit regularization term. And then in this CVPR, a semantic auto-encoder has been presented. This also has a linear objective, and there is an auto-encoder that learns a projection from theta x to phi y, and the projection must reconstruct the original image embedding. So linear compatibility framework has some disadvantages. Usually the classification task is not linear. So if we have only one W that maps images onto the attribute space, we might have some errors in, for example, in this case. But instead, we simply, if we learn multiple W's, we are going to do use piecewise linear compatibility, which will encode, which will support nonlinearity. The only difference between SJE and latent embeddings is we have multiple projection matrices. And each of these matrices, we have realized that they encode a different visual characteristic. So W1 is responsible for detecting long and pointy beak, for example. W2 focuses on seabird with red eyes. Another model that came out in NIPS 2013 was cross-model transfer. So in this framework, this learns a nonlinear compatibility function by encoding it by learning weights using a two-layer neural network, and it also has an integrated novelty detection mechanism. So the argument is, if we know that our test classes are novel, then we can make use of this information also during training. But this requires another level of annotation. We have to know that we have, so training classes versus test classes need to be also labeled like that. Another very widely used model is direct attribute prediction. This has a two-step process. First, it learns attribute classifiers and then combines the scores of learned attribute classifiers to make a class prediction. So this is another set of models follow this idea, actually. Conce is similar to direct attribute prediction. So basically, they learn the probability of a training image belonging to a training class, and then they combine semantic embeddings to make an inference on how much the contribution of scene classes, scene class probabilities as an unseen. So basically, it uses combination of semantic embeddings to assign an unknown image to an unseen class. Another model that I'm going to show results for is Sync. This came out in CVPR 2016 last year. They've built a weighted bipartite graph on the image space, attribute space, and then they also have a graph on the model space. And they have a set of training classes, and they define a set of phantom classes. And the objective is to minimize the distortion error between these two graphs. And a novel class is a linear combination of these phantom class classifiers. Another model is Costa that came out from University of Amsterdam a few years ago. They use co-occurrence statistics of visual concepts between seen and unseen classes. So there is no notion of attributes in this case. The semantic embeddings are inferred from the visual data. As a summary, I have presented some existing zero-shot learning models that can be grouped into 4 groups. ALE, device, SJE, the other one, and SAE can be considered as linear compatibility learning frameworks. And then we have non-linear compatibility learning frameworks, latent embeddings, and CMT. Some of these models have a 2-stage inference that actually were presented in the beginning of zero-shot learning literature. And then we have some hybrid models like Sync. Now I will present some results. So why did we actually propose this kind of an evaluation? The motivations are zero-shot learning is an important direction that has gained a lot of interest. A lot of models have been proposed in the recent literature, but there is no unified evaluation protocol exists, which makes it difficult to compare these models actually. And there are some ugly aspects too. We didn't realize it, most of us, but some of the test classes overlap with ImageNet 1K that is used for training deep networks, which violates the zero-shot learning assumption because none of your test classes should be visible during training time. So the data sets some of the data sets that we evaluated are Sun and Cub. Those are fine-grained data sets, medium scale. And animals with attributes, that is one of the most widely used data sets. It's smaller scale, and it comes with attributes. Animals with attributes 2 is a newly proposed data set that contains the exact same classes as animals with attributes, but AWA didn't have publicly available images, so this one, all the images are downloadable. And then Pascal Yahoo was one of the first data sets. It's very small scale, and most of the classes overlap with ImageNet actually. And then there are a few splits of ImageNet 2. So we use 1,000 classes for training deep networks, and the rest of the images, the rest of the classes can be used for testing. And then ImageNet follows the WordNet hierarchy, so we can use the classes that are 2 hops or 3 hops away from the training classes in the evaluation, or mostly populated classes. So how do our zero-shot learning models perform when there is a lot of, when the concepts are coarse. And then we have least populated classes. These are usually very fine-grained subsets of ImageNet. So one observation that we had, the standard splits that have been proposed along with these data sets. I show results on animals with attributes, but the paper has all the other results. The standard splits that contain, that overlap with ImageNet, the test classes overlap with ImageNet, the results are very high. But if we remove, if we make sure that none of our test classes overlap with ImageNet training classes, then the results drop for all of the data sets. But still, this is a more comparable, I would say. This is fairer comparison for different models. And then we have selected we have split the data sets in 3 different ways for all the data sets, and we ranked the models. In this case, the ranking metrics shows that ALE performs the best in 5 of these cases and the second in 7 of these cases. So this is just another way of showing how the models rank on attribute data sets. And more importantly, I think ImageNet setup is more interesting. So like I said, we split the data set in multiple splits. The first 2 are hierarchical splits, so 2 hops and 3 hops away from the training classes, and the middle 3 are mostly populated 500, 1,000, 5,000 classes, and then least populated classes and all classes. So for the most populated classes, sync model performs significantly better than other methods, but when we consider least populated classes, the fine-grained subsets, and all the classes, then all the models perform very poorly, actually, similar to each other. I'm going to talk about this little bit afterwards when I discuss about open problems. But as a conclusion, this benchmark of zero-shot learning was necessary because zero-shot learning has attracted a lot of attention, and we proposed a unified evaluation procedure. We evaluated 12 models on 6 different data sets, so you can check it out. All the splits, all the features are available, all the code is available. As a summary, we have seen that large-scale image classification fails with lack of training data. And then structured joint embeddings or other models tackles the lack of visual data problem. Attribute, text, and gaze or other, there are other ways I'm sure exists for providing side information. And there are some good, bad, and ugly aspects of zero-shot learning. We should all take care of these so that models that are going to be proposed in the future will be comparable to previous results. Thank you for your attention. So we typically cut the last softmax part of the network and use the activations that come from the previous layers. So it's just an image feature like it used to be, like we used to use SIFT features, for example, to encode. Yeah, so it's comparable to that. Some models, the ones that don't, for example, use attributes, compare, yes, similarities between L2 similarities between image features, but some models actually use image features as one one part of the coin, and they actually project images onto that attribute or side information space, and the comparison between different data points are done on the attribute space. Yeah, sure.
Yeah. Hi. When you are predicting a class for an object that you haven't seen before, you only say it is some other object, right?
You say that these properties that I have learned exists in that image.
And is there a possibility to integrate the hierarchy that you can say, I don't know what animal it is, but I know that this is an animal?
Yeah, there are some works, yes. For example, it might be a completely unknown object. Example images of those objects may not even exist. Like, I remember an example, tiger and leopard. Combination of these two classes can also be considered as a new class. Yeah, so.
Okay, thank you.
Yeah. Thank you.
Right. In the third part of the tutorial, it's my turn to talk about zero-shot learning with localization. And I will discuss, first of all, I will go deeper into why we would like to study further the zero-shot learning paradigm with the direction towards localization. And then afterwards I will analyze a few methods that exist and a few methods that do not necessarily brand themselves as a zero-shot, but that in fact are zero-shot in nature. So again, with some little history or like a little explanation first. Traditional localization works like this. During training, you've got like a lot of bicycle pictures, bicyclist pictures. So for each of these pictures, you've got a user annotating the bicycle, the bicyclist, and at test time inference, of course, you have to infer the bicyclist. So in this picture, you would draw a bounding box around the person on the bicycle. Now, in the zero-shot localization case, you've got a bit of a different setup, right? So during training, you got a set of known visual classes. So you know, for instance, that in your pictures, there are some wheels, so you can annotate them. And you know, in some other pictures, what a helmet looks like. And perhaps in a third set of pictures, you know, like the street. You've got an annotation about the street. And at inference, so you want to move from there, and then define the bicyclist as being a combination of wheels plus helmet plus street. So by this definition, you are going to look in the image and discover where the relevant object is. And then ideally, hopefully, if everything works out perfectly, you will have the box around the object. Now, why zero-shot localization? Let's say we got these attributes, as Zeynep explained earlier. For zero-shot, what is really, really important is to have a set of attributes or a set of knowledge that you want to transfer, and based on which you want to discover things. So let's say we have these attributes. We know that these attributes are correct for what we are looking for. So we have an object which is brown, which is a mammal. It has pointy ears and a curved beak. It has wings. It's hairy, it's colorful, and it has gray eyes. So it has all these properties or all these attributes at the same time. Now, without me showing you the picture, which is essentially what zero-shot localization or classification is for that matter, can you tell me, do you have an opinion of what kind of object could have all these properties? Is there a brave person? No. Well. Yeah, attributes belong to objects, not images. And in fact, the attributes that I showed you just earlier, so all these, are part of two objects, of a monkey and of a parrot. So, sorry for, well, the projector cuts a bit above and below, but the monkey is a mammal. It's hairy, it's brown, it's pointy ears, so that's correct. And at the same time, in the same picture, we know that a parrot is colorful. It has wings and curvy beak and gray eyes. Now, if we were to apply the standard zero-shot classification frameworks, models, we would obviously fail in this task, right? Because we would be asking from the model to discover essentially two different objects. That's why localization is very important for zero-shot classification, and in my opinion, it's a way to actually really evaluate whether your zero-shot model has learned something about the visual appearance of the object, although it has never seen it before, or has just learned to discover some sort of biases. Now, although that's actually a pretty simple scene, it has just two objects, zero-shot localization is even more relevant for complex scenes. Assume I've got this picture, and I have a description here: orange shirt, Sesame Street, sunglasses, and white pants. Can you localize the objects? Probably not, because it's actually quite hard, right? Like, there is a person here which fits the description. It has an orange shirt and the Sesame Street logo. He wears sunglasses, and he also has white pants. But in the presence of so many more people, so many more persons, it's actually impossible to expect the model to be able to retrieve the model, to classify, to retrieve the image, to classify the correct object here. So localization is even more important in complex scenes. Another example on how difficult the task is, because sometimes we don't understand how hard zero-shot localization is. Zero-shot is really hard because the computer has never seen an object. So here we've got a case where the object we're looking for has horns, has brown color, and a white snout. Can you spot the object here? Here? Here, yes. So if we isolate the region in the image, it actually helps us focus. It's like a way to produce an attention map that is essential, is really essential for inferring what the object is. So for instance, in this picture, we can actually ask our model, does the picture look like it has horns? Or whether it's brown in color, or it has white snout? Well, obviously here there is no such thing, right? Like there is no object, and the image itself doesn't have it. Now if we check again the image, and we go to the next location, that's again a negative answer. And then we have to go to a particular segment here, which tells us that what the object is. So actually, if we were to have a very precise segment around the object of interest, we would be able to localize exactly the object and infer its category. Now, what is the special extent of attributes? That's a very important, very relevant question. So, if you have visual details, for instance, floral patterns, these are actually localized in very particular and small areas of the object. So, having a very global description of what the attribute looks like is not always the best way to define the object category, nor to transfer the knowledge. So the floral patterns, the attributes that you want, they have to essentially to be discriminative. So it has to capture somehow a very characteristic information of the visual appearance. It has to be repeatable, right? So here we've got the little flower shape. We might as well have said that we want an angle which is like 128 degrees, but that would not be neither discriminative, not very repeatable. It would appear very rarely. It has to be salient, and also spatially specific. So for localization, we want attributes that are very, in a way, they're self-contained. They're self-contained, they're describable, and can be easily discovered in novel images, new images. However, that's not the only way we can define attributes and visual details. We can also have regions. Now, if we were to have a larger area around the image, around the object, we could still have some more high-level attributes describing it. For instance, here we could have a yellow box surrounding the whole dress region. Now, with regions, these are more salient, and attributes do not have to be visually groundable. So, for instance, here we can say that the dress is actually a retro dress. Now, if we were to go to visual details, that would not be possible. You cannot have a retro visual detail. You cannot have a global, retro is a global attribute, and you wouldn't be able to localize something based on a retro definition. However, what you gain in generalization, you lose in specificity, because retro is not really visually groundable. You cannot actually say that this region is necessarily what makes it retro. It's just the whole feeling is retro. Now, there are several works that have been focusing on both these directions, and I'm going to visit a few of them. So at the level of visual details, we have the bubbles that Zeynep described earlier. So the idea here is that you learn the attributes that are discriminative and machine detectable. And you can do this with either a human in the loop, or you can actually have a machine proposing these visual regions. So how they're doing it in that paper is that they have a sort of a greedy mechanism which proposes a lot of different visual regions, and then the algorithm or a user can say that, okay, that's a good enough type of attribute, or that's not really discriminative. And then it goes on until it finds a set of attributes which is self-contained enough to be able to localize, to be localized. So generally, these attributes are learned to be discriminative and machine detectable, and also semantically meaningful, either by human in the loop. Of course, that's one way to do it. Like the human says, okay, that looks like something that could be nameable. Or you can do it with an unsupervised clustering mechanism. So you would say that I can cluster all this together, and then if the cohesion of the clustering is strong enough, then this must be something which, like this visual pattern, must be nameable. Now, what's really good about it, like some properties, is that it's like this is very spatially precise, right? So we got a bubble around this orange strip surrounded by a black region, or of this yellow belly, or white belly, orange stripes and wings. So these are actually types of attributes that you can really discover in birds and use them. They're very specific and spatially contained. But perhaps the CNN is too invariant. So this method, I think, was in the pre-deep learning era, or they were not really using deep features. Now, whether this can be easily discovered by CNNs, that's a legitimate question. I believe that with perhaps smaller filters, you will have a bigger problem. So maybe you have to have a trade-off there. Now, a problem of this approach is that it's not specifically designed for zero-shot learning, right? So here, the authors focused mostly on learning properties that are specific for describing the objects in the data. So yeah, so the thing is that because the citation is below, maybe I have to push it up so that it's visible. Sorry for that. So this citation was the BubbleNet for foveated imaging for visual discovery by Martin Snavely on ICV 2015, and also another paper on discovering localized attributes for fine-grained recognition, still not visible. Oh my God. Sorry for the overlay, but okay. The most important thing is that you can see the reference. So yeah, this work is on discovering localized attributes for fine-grained recognition. So their purpose was not explicitly zero-shot. Their purpose was to learn visual attributes that would allow for a better fine-grained classification, so being able to predict the genus of different birds. Now, at the level of the visual details, one way to do that, how you can do that, is automatically detect discriminative attributes. So for this, you would use CRFs, so conditional random fields, which you would solve iteratively. And then you will start with a random attribute initialization. However, now in the presence of extensive data sets and a lot of them containing several attributes explaining the different visual properties of objects, not just about the object label, but what the object category looks like, feeling, probably you can do much better. You can, for instance, have a different way to initialize the attributes in that case. However, in the end, with this method here, for discovering localized attributes, they're not necessarily nameable. So unless you have the human in the loop, you're not going to end up with properties that are actually useful for describing the object. They can be good for predicting the object. They can be good for creating a caption, which is very popular mechanism right now. But sorry, it's going to be good for classifying the object, but it's not going to be good for generating a caption. So to convert them to nameable, a human needs to approve, to discard, or to rephrase that, to discard the visual properties that don't make sense. And the CRF is composed of these two terms here. Essentially, the unary term conditioning on the image and the object, and then the binary term maximizing the compatibility between different visual properties. Another work which does the opposite the opposite paradigm of zero-shot localization is the one proposed by Lee et al. In our group at the University of Amsterdam. Title Attributes Make Sense on Segmented Objects, presented in CV 2014. And well, it's the first work that did a region-level attribute-based localization. And the goal or the motivation was explicitly what I showed you in the picture with the monkey and the parrot. So the goal is actually to find the object in the image which can be described by the respective description. So for this work, the first step is to extract regions for localization. And back then we used the CPMC regions proposed by Carrera et al. Let me fix that also. The CPMC stands for Constraint Parametric Mean Cuts for and then after we compute the essentially what are object proposals, we're solving for a structured problem, for a structured SVM problem. So f of z comma y is essentially our compatibility function that Zeynep described earlier. Then we have the bilinear model of theta on one side. W is the matrix that we want to learn, and phi the attributes. And in the end, we're solving an L2 regularized regression problem. Now, after we do that, we have trained for that. We can use A-lead attributes, so we don't propose a different classification model, and we do a per region maximization. So we focus on computing the compatibility score for each of the 500 regions here iteratively, and then in the end we keep the maximum one. So the zero-shot localization is, here is done as structure prediction. It's cast as a problem of structure prediction. And the regions are latent variables. Here we see some examples. Actually, the problem managed to discover, to localize the object of interest. The model discovered the object of interest quite all right. So I'm not sure if it's really visible here, but with an IOU of 83%, it correctly found the white-eyed vireo object with the attributes of having O-like shape, brown eyes, multicolored tails, or bills. And here are some more good examples of detecting northern waterbrush and groove-billed Annie with a very good IOU, higher than 50%, that it's in Pascal VOC challenge like tasks. Now actually that's actually quite impressive if you think about it. So the model has never seen a white-eyed vireo, neither a northern water thrush nor a groove-billed Annie, but it still manages to localize them, to find them, right? So this means that our zero-shot model has learned something about it. It's not just noise, it doesn't focus on the background. Of course, this doesn't always work as accurately, so in some cases it does discover the correct class, like in the case of the Western gull here, but the IOU, the intersection over union overlap, is less than the commonly accepted threshold of 50%. Here it's 46%. In some other cases, the prediction is even wrong. So a belted kingfisher or a grasshopper sparrow examples here were not discovered as they should. So with zero-shot localization here on a region level, we have some evidence also for accidental zero-shot recognition. Here we're seeing that sometimes the model is actually able to discover the right class, although the intersection over union is too low. So this means that perhaps the model has overfitted its representation or its embeddings so that to use only a few parts of the object and accidentally have a better performance. Now, for the zero-shot localization by attributes, you have a dataset DA, and you're maximizing losses on different datasets for different attributes. And for the zero-shot inference, you've got different attributes that are detected as histograms, and then you maximize over different regions. And then, for instance, you pick the one that is maximally activated. So another interesting work is the localization, another interesting perspective is seeing the localization as retrieval. So in the localization as a retrieval case, we start from a query, like the Eiffel Tower here, and the goal is to find the target in the image. So essentially this amounts to ranking sliding window images. So for instance, we could start cropping different objects, like with object proposals, and then thousands of images are generated. So from a typical, like from selective search or from edge boxes, you get from 100 to 2,000 boxes. And then in the end, you want to learn a scoring function, which has two inputs. The first input is the query image, and then the second input is the sliding image here, the sliding window. And then the output, you want it to be the similarity between input 1 and input 2. So this is actually how a lot of modern systems train themselves for supervised classification. Let me push again, the reference to be visible. Now, this work is an example of a work which is not branding itself as a zero-shot localization, but it is one. And it was an oral last year. So the work is natural language object retrieval by Hu et al., which was presented last year in CVPR. This is very similar to zero-shot localization here, but input one here, instead of being an image, like here we would have an image, right, in the query, right? Now, instead of being an image, it's a text query. Since now it's a text query, we can proceed as follows in a similar way. That's not really stopping us. So we can decompose the learning objective as by the Bayes rule into the different learning weights, and then rank sliding images. So the scoring function measures the similarity of the image to text. You're learning a textual to visual embedding. Their model is summarized here. So first you would have the input image, and then you would have a set of object proposals as candidate locations. And then your natural language query is added to a spatially recurrent coordinate. After pooling globally on the image level and on a local level for different object locations, you can train a compatibility function that returns a different score per region. This is actually also a very interesting work that generalizes on the previous one that we were doing essentially with just attributes, because this is about natural text. It's not just about a set of predefined words, essentially, that we have to define in the training set, in the training time. So the semantic attributes here that we had, and also this works has, is things like hat and white, but they also have special attributes like right or on top of or below, and you can also have global context. So for instance, you would have a query white hat, and then the object can localize the white hat. Or you have a query window with closed curtains, and then the model is able to detect the particular region. In the previous work, the descriptions were constrained to be much simpler, so you would have white or you would have red wings. So here is a generalization. Now, another way to do a very similar thing is to consider video. So you can have a zero localization of videos, also known as tracking by natural language, which we presented again. Which was presented this CVPR. So in this case, we say that tracking is one of the most traditional methods, tasks in computer vision. And the problem is that they always require having a bounding box around the object region. So what we propose instead is that we can define the target, not as a bounding box, but as a language description, which is actually what zero-shot does. And then after that, you can actually continue tracking the object. For instance, you could have tracked a little green person with the Bayes robe, and the model will continue following the object. Now, why would you do that? That's actually where it gets interesting here, and that's, I think, in my opinion, one of the best use cases for zero-shot localization. So imagine, for instance, that you have your autonomous car. It would be much better, it's more, not better, but, well, I guess it's more natural to ask from your autonomous car track the yellow taxi or your left. You wouldn't like to, like while driving, to start drawing boxes around. But it also allows for some novel applications of tracking because you have no first frame requirement. So when you define things by text, you can start tracking in the middle of the video. In traditional object tracking, you have to have the first frame where the object appears, and then you draw a box. So here we can have a continuous video feed. Moreover, you can have multiple videos and multiple targets being tracked at the same time, because with one sentence, you can follow in the different objects in multiple videos. Whereas with bounding boxes, you'd have to draw a different box for each video separately. In the end, we also found out that this allows for more robust standard tracking, and because the tracker adapts to appearance variations. The model for this paper was a cascade one, composed of 3 parts. In the first part, which is the model 1, the simplest case, the text query goes to an LSTM, where it gets embedded. Here is the technical novelty of the paper. That's dynamic filter generation, which receives the text embedding and generates dynamically weights. So normally, after training, the weights are fixed. In this work, we generate new weights for every new instance, depending on the text query. Based on the filters, these are visual filters, so these are visual filters generated, conditioned on text. We generate the visual filter with which we convolve the frame, and they can detect the object, being the box with the maximum accuracy, the maximum score, and we do it for each frame independently. Now, of course, you can take the first frame object detection and then apply a standard visual object tracker, or you can combine both, and this is what Model 3 does. A very similar work presented also in this year's CVPR is person search with natural language. In their case, they have a more constrained setup. It's not about the general object tracking, it's about pedestrians. But you have a very similar problem definition, as in the query description is the woman is wearing a long bright orange gown with a white belt as her waist, and then the goal is to find the person that fits the description. And then, all right, yeah, sorry. Is it visible? Yeah. So the title for this paper is Person Search with Natural Language Description by Li et al. And was presented in this year's CVPR. So for instance, we can see some examples here of object regions of people and the descriptions that accompany them. And we can see they're quite elaborate. Now, how you can do that is that you first extract region proposals again, so that's a common theme. That makes sense. I don't think, without having empirical evidence, I don't think it would be very easy to do this type of search without object proposals. So you have to have some sort of notion of what an object is. Then you compute word-specific dynamic filters, very similar to what we did, and compute word-image affinity. So again, you compute a compatibility function which combines the visual information, the textual information in a common space. So my time is almost over. These were a few works on zero-shot localization. What would be the takeaway message here is that attributes is very important to understand that belong to objects quite often, not just images. Sometimes if they're global, they belong to images, but usually attributes are about objects. And objects can be large, can be small. In one image you can have multiple objects, so it's very important that we localize them. So zero-shot localization is a very natural extension, and object tracking by language description is a very novel and relevant direction, also connected to video detection. So thank you very much. Do you have any questions? Any questions? Yes. All right, that's a very nice question. So you're talking about this one or a work or another work? Here. So if the text has to be adaptive. So here it doesn't have to, because you got a single image, and that's a bit of a kind of an academic problem here, of course, because why would you search an object by description on a specific image only? Probably you would like to do this over multiple images, and then you would need it to be adaptive. But for a single image, it doesn't really make sense. White hat is what you're looking for. However, your question is very relevant for visual tracking by natural language, because the thing is that when you've got a caption like "man with blue shirt and backpack next to a tree," is relevant perhaps to the first frame, but not necessarily relevant for the 50th frame. And then you do need the text query to be adapted. And that's why in this work we propose an intention MLP, which places different importance on different words depending on how relevant they are for describing the object over time. Other questions? Well, I guess case will continue. Do you want? This? Oh, yeah, of course.
So my name is Snoek. So we have covered classification and localization, and actually Stratus also indicated that localization soon ends up in retrieval. So I'm going to talk about retrieval. What's going on here? So we are here in the program. So as I mentioned, so to give you an insight, what is the difference between classification and retrieval? So in traditional zero shot, we want to classify tests, videos, or images by some predefined mutual relationship between the classes and the attributes, right? So here we have a piece of the table of the attributes with animals with attributes data set. So somebody has to specify that the zebra is striped, is black and white colored, has a tail, has pointy ears, and so on. So in retrieval, we typically don't have this class to attribute mapping available. Instead, we typically rely on a description, like the natural language description that Stratus showed. Now, there is a clear relationship with work in the multimedia community that's related to cross-modal retrieval, where it's a well-studied problem where you go from text to images, or from text to music, or from text to video, or from music to text, or from images to radar, and so on. And so here we will focus today in the retrieval session, we'll focus on text to visual information and vice versa. So here is one of the earliest work I am aware of on doing text to image, so to say, or zero shot image retrieval. And basically they start with like a paragraph of a snippet of a Wikipedia page on the history of southern India, and then they retrieve those 5 images based on the textual description only. Here's another example from ICV 2015, where folks at MIT looked at Harry Potter movies and aligned fragments of the video to fragments of the books. And this is another example, and lots of work actually has been going on in this area as part of the TrackFit multimedia event detection benchmark, where people have looked at, given the description of a particular event, can you find the corresponding videos in a large collection of video clips? So what is the problem statement in zero shot retrieval? Well, essentially it boils down to the following things. So we need to align the visual and the textual representation to a common space, right? Now, the challenges here are that we have different dimensionality. So a visual feature typically represents like a pool 5 layer, and then a textual representation typically has a bag of words. How can we bring those two together? So basically there are 3 approaches that have appeared in the literature. So the first one is known as sort of like low-level alignment. So you try to align the 2 modalities directly in the low-level feature spaces of the 2 modalities. So typical methods are canonical correlation analysis, and also like things like cross-media hashing. Now, this is arguably not the most effective space to learn the correlations, right? Because it's very hard to interpret. Nonetheless, many people try this. So how do you go about? So you have an image that is represented in some feature vector, and you also have a text representation represented in some feature vector format, and then hopefully you hope to find that this text snippet matches to that image, but how to get them into the right space, right? So the image is in the image space, the text is in the text space. How can the 2 be aligned? Now, one of the most popular methods is canonical correlation analysis, and basically what this method tries to achieve is, given the input space of the image space and also the text space, find in each of them that subspace for which the correlation between the 2 is maximized. So that is essentially the goal in canonical correlation analysis. Here is the equation. Is a pretty old technique, but still used very often. Now, so that was low-level alignment, so directly working on the low-level feature space without any means of interpretation. Then there is also what we call mid-level alignment, and this tries to align 2 modalities that sort of like at mid-level features. And these mid-level features are typically extracted by autoencoders or topic models. Now, topic models are well known in text analysis, so it's a very good approach to encode text. But in low-level visual feature space, they have limited meaning, so it's very hard to introduce topic models on top of visual responses. And also deep autoencoders are less suited for small data sets. And then there is a high-level alignment or semantic alignment. And the goal here is to embed both the images and the text in the same semantic space. And for example, this can be done by defining attribute classifiers or concept classifiers. And then the semantic space is spanned by the attributes for both the visual data as the textual data. So here is an example. So we have an image space R, and we define a bunch of concept classifiers. We use the same concept classifiers for the text, and then each media item becomes a point in this semantic space, and we have a way to compute their similarity. This is a nice idea, originally proposed in ACM Multimedia 2010, and also appeared in PAMI some years ago. The problem here is that you still have to define, annotate, and train the concept classifiers of your semantic space, right? So there's still a lot of manual labor involved before you're up and running. So I want to present some work where we learn the semantic alignment instead. So the research question here we started with: can we learn the alignment from, in our case, videos and their captions? So videos are everywhere on the web, and typically users will add like sentences to the video describing the content. So here, example, crazy guy doing insane stunts on a bike. And this caption usually highlights the key concepts or key attributes in the video. Now, what people typically have been doing is to create sort of multimedia embeddings, right? So we have a visual projection matrix W and a textual projection matrix A, and we want to combine them into one joint space, which we call our embedding, and this relates the multimodal input, so to say. Now, what our approach, what we dubbed video to vec, does is we embed the story or the caption of a video in such a way that we preserve the video descriptions, while at the same time also recognizing the terms visible in the video content. So how do we go about? Well, this is basically the basic idea. Small animation. So this is the video with a bunch of terms or attribute classifiers that we built on top of it. And now we can say, well, we can build a classifier for each term individually, or we start to combine them. So, for example, bike and motorcycle becomes a pair, up till the point that we combine everything. But what we try to achieve is we learn automatically which terms or which attributes to combine in sort of a new attribute. And combination is useful because you will get more examples for free, and you get a better predictor. This is the main idea. So why is this important? Indeed, the number of classes is reduced, so you get a more compact representation in the end, and you can train classifiers per group of terms, so more examples are available, better predictability. And the best of it all is it comes for free via web supervision. So, key contribution here is joint optimization. So we jointly optimize descriptiveness and predictability. So we do that by combining a combined loss, where we define sort of like embedding S, which is the joint embedding for the predictability and the descriptiveness. Each has their own loss, and we combine it in a bit. So the first objective is that the descriptions, so the attributes that come out of the embedding are descriptive. So they should be interpretable, right? And that is what this loss tries to optimize. This is essentially latent semantic indexing, but then with an L2 rather than an L1 norm. And this is the predictability loss of video to vec. So also nothing fancy here. We try to just predict as good as possible the label given the feature, given the features and the training data. Now, how do we train this embedding? So we start with a set of videos and their captions, which we collect from YouTube, say. We encode each video with our favorite feature, independent actually of what feature you use. You can use old school features, pull 5 layers, what have we. You can even do multimedia if you would want to do that. And then we encode the video description, so the captions that come with the video, with a simple bag of words vector. So how do we get the videos? So we collected a video dataset, about 46,000 videos with 20,000 unique terms. And we filtered we did some language processing on the captions to get rid of the obvious mistakes, so to say. And then the training is quite straightforward. So we optimize each of the loss functions separately, and also we combine. We also optimize the entire thing. So we do it in an iterative way and using just a stochastic gradient descent. This is how it works. So we have a certain video. We compute the visual features and project it to our semantic embedding SI. Then we can translate this embedding to text by using the textual word projection that we learned. That gives you, like, this shows what are like the attributes that pop up in this representation, and this you can use for matching with a query text using standard matching metrics, or like cosine distance. In fact, there was a paper at this CFPR by Hussein et al. That also learned the metric rather than using an off-the-shelf metric. So here are some examples. So this is the input video, and this is the ground truth description that comes with it. So in this case, it's for an event called non-motorized vehicle repair, and this is the automatically derived attributes that the embedding has learned. So without knowing, without ever having seen this video. And indeed, some of the highest scoring ones also make sense. Here are some another example. So horse riding competition, and here jump and horse indeed are the ones that pop up clearly. Last example, renovating a home. Again, we see relevant concepts pop up. Of course, these are selected examples. There are also some attributes that are irrelevant to the category of interest, so it's not perfect. It also still makes mistakes, but you get the idea. And actually, it works really well. So this is a comparison on an event detection benchmark, and it even outperforms CFPR 17 paper. So this will appear in PAMI soon. Okay, this is all great, but this only gives you like a global classification of the video. So Stratus has just explained the importance of localization and how that adds a lot to the semantic interpretation for zero shot in computer vision. So in the next chapter, I will add localization to this embedding, and this is a paper that will appear in ICCV in Venice. So what many people do in zero-shot classification, in this case zero-shot action recognition, is they represent the video by a set of attribute classifiers or object classifiers, but the position of all the classifiers is considered irrelevant, right? So here's a keyframe from a video on Tour de France cycling. So we know that there's a bike, a motor, a crowd, a polka dot jersey, a road, and so on, but we don't know where these objects appear in the image. And actually, many of the state-of-the-art approaches don't even need it to get to their good numbers. So here's a typical approach called objects to action. So this is zero shot. So how does it work? For a given test video, you compute all relevant objects. Now, suppose you have 1,000 ImageNet objects as classifiers, and that is your representation. Then for each of these classifiers, you compute like an object action affinity. And this is typically achieved with some word-to-vec embedding using a text corpus. So in the text corpus you find the correlations between objects and actions, or nouns and verbs. And these affinities help you to select those objects that give you the best response for a particular test video, and that's how you find the action of interest. But again, this uses no localization information whatsoever. It's pure classification based. So the proposal we make is first to identify two types of objects. So there are background objects and foreground objects, so to say. And the foreground objects are typically more important, or the interacting object. And the position is key for relevance. So if you have the action cycling, it's kind of obvious that bicycle is a very relevant object, right? But the position of the bicycle relative to the actor is also very important, because this bicycle is far more important than this bicycle that is accidentally in the background. So the position is key for relevance. So we came up with a spatial aware object embedding that basically does three things. So it encodes where the actors of an action are occurring in the frame and in the video. It has a notion of where the relevant objects are in the frame. And it also verifies whether the actors and objects are in spatial relationships that make sense. So how do we get there? Well, for the actors and objects, we use as side information basically an off-the-shelf object detector for images. So in our case, we do faster RCNN. So we pre-train it on ImageNet and MS Coco. So for each of the objects in MS Coco, we generate bounding boxes and scores. And the person class is simply used as the actor classifier. And for each of the actions of interest, we can use word2vec to select those objects which have the highest affinity, the highest similarity with actions of interest. We also define a simple grid cell of 3 by 3 cells, where we encode where objects appear relatively to an actor in the MS Coco dataset. So this gives us sort of a prior that a horse tends to be under the actor when you are riding a horse. A bicycle tends to be also close to the actor, so in this area over here. A traffic light is typically top of the actor, and a skateboard is typically below or on the actor. So these kind of priors we encode into our embedding. So how does it work? So we have a simple scoring function. So this is all still 0 shot, so nothing is learned. So we compute, given an input frame, we want to extract this green box over here. So we first run our actor detector, and the brighter the spot, the higher the probability that it is an actor detector. Then we have learned for the action riding a horse that horses is an obvious object to detect. So here we also list the horse detections with the highest scores, and then we correlate the actor and the object that are most relevant, and we look for the most logical spatial relationships to reinforce that this is indeed the most likely location of the action in this case. Now this is for a single frame, then we can also link those boxes over time using a dynamic programming approach based on the Viterbi algorithm that basically takes the boxes with the highest scores and looks for the ones in the next frame that have the highest overlap with that box, so as to build sort of like a tube through a 3D space. So here are some qualitative results. So you say like riding a horse, so it finds the action, but it also finds the objects of interest. So this works with like, this is the query, riding horse, and it will find the red box, and it gives you the blue box as bonus. Here's another one, skateboarding, with the skateboard visible and selected as the most likely object in this case. And here, this is an interesting one. This is a failure case. So the action here is kicking, and the embedding has found that tie is the most likely object that corresponds with this action. So remember that so tie has a connotation with soccer, like a tie in soccer is a 0 to 0, for example. But here's some ambiguity, because a tie is also a thing you wear around your neck when you go to a bit more formal occasion. And that's one of the detectors that is in the set of AT-MS COCO detectors. So because of this ambiguity, it is firing on the wrong box. So in this case, on the referee rather than the actor doing the action. So this was nice, and then this inspired us to also sort of like introduce a new way of spatiotemporal retrieval. So here we look for a backpack that is on the actor. So we can search for actor and object combinations with certain spatial configurations. So this is a new type of search in video without the need for any examples. Here's another example where we can also specify the size of the object relative to the actor. So in this case, we look for a sports ball that is rather small, but it is on the right of the actor. So this is a new way of zero-shot retrieval, so to say. So it does use site information, and so it does use faster RCNN detectors, but those are trained on off-the-shelf image sets. So for video, it has never seen any video example in all of its development. So conclusion on zero-shot retrieval. I think semantic embeddings are the best way to align visual and text modalities. So we proposed one solution to achieve it, and it can be learned from webly supervised classifiers. So no need for any manual annotation or specification of a class to attribute mapping. If you want to make those embeddings local, off-the-shelf object detectors are really good nowadays. I mean, we have seen it at this conference. The progress in object detection is actually astonishing. And just taking them off the shelf, they can do magical things also for things like action localization without video examples. And what this enables is spatiotemporal retrieval in video with position and size qualifiers, and soon more elaborate spatiotemporal reasoning, I'm quite sure. So with that, I would like to end this section on retrieval, and I'm happy to take any of your questions. For which one? Yes, it's in ICCV, so it's this is the title. To appear, yeah, ICCV is yet to happen. Yeah. Any other questions before we go into the coffee break? If not, then I would like to thank you for your attention once more, and we reconvene at 4 p.m. Sharp. Thank you.
Thank you for staying, although it's much nicer outside. So in the morning earlier, I presented zero-shot learning for image classification, and I mentioned that I will talk about some open problems for zero-shot learning in image classification, and this is that part. Oops. Anyway, I can use this, the keyboard. Okay. So this is a picture from earlier again. Zero-shot learning task tries to solve the problem when the number of images are, so the fine-grained subsets of large-scale data sets. So we have very few images available from some of the classes, and at test time we have a strong assumption that the test classes are going to be completely disjoint from training classes. But the problem is bigger than that. We want to generalize to the entire data distribution. So like I said, in zero-shot learning, we have a set of classes at training time along with their attributes, and we have visual data for these classes. And at test time, we have a completely different set of classes whose attributes we know. That's how we can do the inference. On the other hand, for generalized zero-shot learning setting, we have both the training classes and test classes at test time, which is a more realistic setting. So for evaluation in the zero-shot learning setup or generalized zero-shot learning setup, we propose to use per class top 1 accuracy, which counts the number of correct predictions and normalized by the number of samples that belongs to this class. And this ensures that all the classes will weigh the same. So no matter whether the classifier is making correct predictions on highly populated classes or sparsely populated classes, all the classes will weigh the same. It's important to remember that. And then for generalized zero-shot learning, there are 3 accuracies that we propose to evaluate. The accuracy on the training classes, the accuracy on test classes, and normalized by the sum of these two. That ensures that seen and unseen class accuracies will weigh the same. So earlier I had presented zero-shot learning models, and we grouped them into 4 categories. We had linear compatibility learning frameworks. We had non-linear compatibility learning frameworks. We had 2-stage inferences, so we were learning attribute classifiers and then making a prediction, class prediction based on the attribute scores. And then we had hybrid models, so linear compatibility learning frameworks combined with 2-stage inference. So for evaluation, we used again 5 different data sets, and we chose them because Sun and Cub are fine-grained data sets that are medium to large scale in terms of number of classes and also in terms of number of images. Animals with attributes is medium scale but coarse-grained data set, and A Pascal A Yahoo is a coarse-grained and small scale data set. And the largest scale data set that we have is ImageNet, and we proposed 4 different splits. One of them considers all of the remaining classes that we don't use to train deep nets, and then classes that are hierarchically 2 hops or 3 hops away from the training classes, and then most populated or least populated classes in ImageNet. So earlier I had shown this graph. This is I say generalized zero-shot learning, but it's a mistake. Zero-shot learning setting on ImageNet. So these models, the ones that I presented, compared this way. So some of these models, for example, Mensink, performs significantly better than others when we consider most populated classes. But we also, like I said, are interested in generalized zero-shot learning setting. And let's see how the graph looks like when we consider all of the classes. It's quite different. So the model that performs the best doesn't perform well. The other, in general, the accuracy drops significantly. So this was around 16%, and this is around 3%. This is top 1 accuracy. So there is a problem here. So we tried to see what the problem might be. One aspect is in ImageNet there are ambiguity in labels, so people don't report top 1 accuracy mostly. They report also top 5 and top 10 accuracies. So if you look at the graphs for top 5 and top 10 accuracies, the results look better. The accuracies are higher. And the models, for example, Mensink, that was performing really badly before, appears in these graphs. But still, compared to zero-shot learning setting, in the generalized zero-shot learning setup, models still perform very poorly. So we decided to look at accuracies on unseen classes and seen classes separately to see where the problem might come from. So in these graphs, they are evaluated on animals with attributes and birds data sets, so like medium to large scale attribute data sets. The accuracy on unseen classes for most of these methods is quite poor because the images are embedded close to seen class embeddings. This is a problem. So the seen class accuracies are much higher than unseen class accuracies, but what we are interested in is the average of these. So that's why we proposed harmonic mean here. So the aim for zero-shot learning or generalized zero-shot learning should be to improve the green curve here. So to balance the unseen and seen class accuracies. Again, if we look at ranking of the models, if we consider seen class accuracies, Conce performs the best, and then unseen class accuracies, ALE, the linear compatibility learning frameworks work the best. And in harmonic mean, usually the models that perform well with respect to unseen class accuracies stay performing better, basically. But there is still some differences. So as a conclusion, in generalized zero-shot learning setting, this setup is very challenging, but it is more practical. I think we should focus on generalized zero-shot learning for practical reasons. And one problem is unseen images, so the images that come from unseen classes are embedded close to seen class embeddings. And the results are much lower than zero-shot learning results, so which indicates that there is a large room for improvement. I would suggest you take a look at this paper. We have a journal version that is in archive that has much more analysis on many models and these data sets, and we have quite a few insights. We don't propose a solution, we just point out to a problem. So please feel free to work on this problem so that we can all together solve a practical task. That's all from me. Thank you for your attention. If there are any questions, I would be happy to answer.
All right, so I'm going to delve more into now open problems from my point of view that complement Zeynep's perspective. So as a short recap, zero shot involves two steps, two parts. One is the training part, where you got training in your dataset DA, where you learn attributes, 1, 2, 3, K. These attributes have to generally be defined manually. So somebody has to decide what these attributes should be. And then based on these learned classifiers for attributes, you can combine them such that you discover their strength, their activation potential on a new image, and then perhaps say something about that image. So for instance, this is an African elephant because it has a big ears instead of smaller ears, or because it's very large, etc., etc. Now, some examples of such attributes are those. So you can have a curved bill. That's one type of attribute. Or along a lula, or an orange chest. So I'm pretty sure that you're not ornithologists, so maybe you don't really know what is an alula, and I'm sure I don't know. Some of them are clear, like the orange chest or the curved bill, but it's actually pretty obvious that not always attributes are going to be easily defined a priori. Sometimes you need to have a human telling you at training which attributes to learn, where to focus, etc. So why not try having some knowledge transfer? Essentially, your shot is about transferring knowledge from a source domain, where you know a lot of stuff, to a target domain where you know visual examples. So why don't do it with interaction? Why not have a human in the loop who is going to take some critical decision to help the system learn better and faster? Why would you need that? Well, attributes are often ad hoc. So choker hold, or rose and canary looks, or velvet touch, all these are attributes, right? So these are attributes that I recovered from, I think, eBay for clothes. Now, why not like have a crocker hold? Why not something else? Well, the attributes don't have to be strictly defined. Sometimes it's nice to give the freedom to the user to decide which ones to have. For instance, here we have the ankle attribute, or ballet flats, or court shoes. So it's very hard actually to have all possible attributes predefined. That's perhaps an even greater labor than just annotating the object categories in the first place. So in that case, what we can do is have active learning during training, where here in this step where we learn attributes, we've got a human that intervenes. Now, there have been some works that involve a human in the loop and make things very practical. So I'm pretty sure, like, if you work in a company, definitely having a human in the loop is very relevant for you. So in this work, you got the zero-shot with independent attribute prediction, so the original zero-shot model, and you got online incremental learning with self-organizing neural networks. They use a linear SVM for learning the attribute classifiers, and then they divide the images into positive and negatives. This is like a 5-year-old work. Ever since there've been more. So you can also interact with the local attributes. That's the work that I showed you earlier on discovering localized attributes for fine grain recognition. So in this work, discriminative localized attributes are anyways discovered automatically, so the machine is able to detect those. But as we saw earlier, not all of them are going to be useful for a human. So perhaps this is too much of an attribute, whereas like that's too generic or too large, or it exists in many different bird species and not in a very consistent manner. Whereas here, you've got more specific attributes, better attributes, and then the human can actually tell you, okay, this attribute is about a red head next to a white body. So in this work on discovering localized attributes for fine-grained recognition, you have some sort of recommender system prioritization where spatially consistent features are shown first to the user. That actually enables faster learning. Another method is considering relative attributes, and this is actually very, very relevant. The reason is that attributes are not always easy to define in an absolute manner. See, so if you have an attribute young or old, what is young and what is old? So like Sean Connery is definitely older than Brad Pitt, but also Brad Pitt is older than Justin Bieber. So maybe what makes sense is actually to define attributes in a relative sense. To achieve this, in the work of Tariq et al. On relative attributes for enhanced man-machine communication, a learning to run formulation of relative attributes is defined. This is the learning to run SVM formulation. And then you have interactive search. So you learn attributes offline, and at inference you rank images according to the relevance, and the user indicates the ones that are where the relative changes exist in top ranks. So this involves also an active labeling process. So intuitively this reduces to having a query like black shoes, and then a feedback from the user says, okay, I would like to have more formal shoes than those here, or shinier shoes than those here. And then, well, ideally, hopefully, the system learns to return relevant results. Another very interesting work, which in my opinion relates to the generalized zero-shot learning that Zeynep presented, is predicting unfamiliar classes. So what happens if you've got an open set of classes at test time? You don't have it limited into just 20 or 30. In fact, this is a much more realistic scenario. Probably, like knowing already you have a particular number of unseen classes is already a piece of information, perhaps. So in this work, on attribute-based detection of unfamiliar classes with humans in the loop, 4 years ago, they have an open set of classes at test time, and they've got a formulation which is slightly different than zero-shot, because they don't know they don't have any attribute to class mapping. They just assume that a familiar class is the probability, the product of the probabilities of the one minus the probability of seen classes, and then they threshold things. The user corrects misclassified attributes and goes so on. The model is essentially a Bayes rule decomposition of the probability of a class being unfamiliar or not. So where the user, like certainty, is conditioned on the attribute in the image. Generally, what we can say about knowledge, about sharing knowledge, is that knowledge is not static. However, in what I've seen in many works is that, well, we have 200 birds and 50 attributes, or we've got like chairs and then we've got like 200 attributes. But not all problems are as static as this type of descriptions. So for instance, every year, new and larger data sets pop up. So very few of the approximately 90 data sets in the last year include data sets such as kinetics, which contains, I think, 300,000 videos, M2Chi, Scannet, Oxford Robot Car, Cityscapes, Label Me Facade. Besides that, Wikipedia expands by 10 edits per second and 750 new articles per day. So if you would actually consider Wikipedia, some works already do that. They consider Wikipedia as a side information database. What would you do? Would you like have to learn new models for every day? That's a bit extravagant. Should we discard then all datasets, or when new knowledge appears, or can we actually actively engage with external knowledge sources such as Wikipedia, so that QA is not constrained to what we've seen during training? So do we want a more adaptive, more dynamic system? Some external data sources. Well, WikiHow. Do you know WikiHow? Can you raise a hand if you know WikiHow? Nobody knows. Okay. So WikiHow is a Wikimedia type of website where some volunteer gave instructions on how to do particular types of tasks. So for instance, funnily enough, you can go to WikiHow and learn how to get married. So in step 1, it says you have to find a partner. Step 2, you have to find the best man. Then book a church or a chapel or the municipality, the town hall, and so on and so forth. So WikiHow is an external source of information that one can use. Wikipedia is a similar type of source. Wikitravel, DBpedia. DBpedia is a more machine-friendly type of database that essentially contains the same information like Wikipedia. EventNet is a dataset which combines WikiHow with particular video categories. So a few ways only that somebody can exploit external sources is with active learning, like what we saw earlier. So you can have an active learner working all the time and updating your model. But also you can have knowledge graph parsing. So there was an oral in this CVPR, the more you know, using knowledge graphs for image classification by Marino et al., who used knowledge graphs specifically to be able to classify images better. But you can also do that for, of course, question answering, visual question answering. And if they haven't done that, probably they will in the next conference. And in fact, avoiding catastrophic forgetting is also some sort of exploiting external data sources, because you can continue keeping your old knowledge intact while expanding the model. So specifically for the case of the 3 paradigms of learning, zero-shot learning, transfer learning, and active learning, a legitimate question is whether we can actually integrate it through these 3 paradigms. And this is something that we did, myself and colleagues, on this work on active transfer learning with zero-shot priors. So reusing past datasets for future tasks. And our idea, our motivation is exactly what we said earlier, what I said earlier. So, okay, ImageNet exists. Why should I throw ImageNet for when the open images is announced, or for the kinetics data? Can I actually reuse these datasets, even if the tasks, ImageNet is about like fine-grained classes, let's say. Even if these classes are not relevant for my new dataset, perhaps I can reuse this type of annotation, these millions of dollars spent to create this dataset, to improve my learning for my new dataset. So in this work, we recycle all datasets, and ImageNet, like that, ImageNet is not going to be obsolete in the future. Another thing is, for instance, we can enrich current datasets by segmentation propagation. So a schematic of the approach is like this. You might have all datasets, like ImageNet, Pascal, Microsoft Coco, or Flickr. Based on this, you can create some zero-shot priors from your source tasks. So the labels in these datasets are your source tasks. From Pascal, you see, you know how a bicycle looks like or how a car looks like. And then you have a new class, like let's say BMX. Now I searched ImageNet or these datasets, I couldn't find BMX. BMX is a type of bicycle. But let's say that I'm a company, I'm like building better visual search engines, and then my user wants to be able to discover BMX bicycles. How is he going to, or she is going to do that? Well, You can reuse information here, because for BMX bicycles, you don't have any annotations. You can reuse the annotations, you can reuse zero-shot priors from these data sets that you do have, and then an annotator can guide the process accordingly. And then you can actually classify novel images for your novel classes. How to transfer? The zero-shot model that we use is Costa, because that was the easiest for us. It was a prior work that we had done. For Costa, you have the image and then the models that you have already learned, together with co-occurrences. And the co-occurrences you can find from all data sets or from like Google. And then the active updates are defined as an iterative learning procedure. So from the zero-shot model, you say that BMX looks a lot like bicycles from my co-occurrences, or you can of course use word2vec, ALE, device, any type of model. The zero-shot classification is not something that we are working on in this project. And then how to actively learn, so how to do the iterative updates. That is the technical contribution, which is actually very interesting. So simply speaking, we found out that to have optimal active learning for a support vector machine framework, so not for deep learning necessarily. That's something that I haven't worked on yet, or I haven't seen anybody else working on. But for support vector machines, we found out that sampling from the margin is something that is important, but a lot of people have proposed that. What we propose is that you have to make sure the positive versus the negative labels after your sampling, after every iteration, has to be balanced. So you have to keep running some sort of log of your label sampling likelihoods. And the reason why you do that, we prove why this has to be done like that. This is based on two conditions, maximum conflict and label equality, that can be derived by the dual formulation of the support vector machine. So from the maximum conflict, it says that to maximize the objective of the support vector machine and to keep the label equality, you have to have balanced samples. So yes. So what is very interesting here is that if you actually run this at test time, you can see that a boat, this is a zero-shot class. We don't know what a boat looks like, but at time step 0, it returns a water scene, most probably because the zero-shot priors are good, but not good enough. So the zero-shot prior tells you that the boat looks like water. So in the second step, your active sampler is going to sample something near the boundary, near the margin. It selects another negative sample, but now our active sampler knows that we have selected 2 negative samples, so it gives a priority to something which is most probably going to be positive. So this means that we have to sample now from very close to the margin, so that this makes sense. And indeed, we sample a positive sample. Now that's like a ratio of 1 to 2. The active sampler decides to go for a negative sample, then a positive, then a positive, then a positive. And then we quickly find out that our SVM classifier approach converts very fast. What is very interesting here is that indeed, in this 8th step, we have 1, 2, 3 versus 1, 2, 3, 4. So almost 50% positive and negative samples, which is the label equality. And the same holds for the second row. Now, why we want the label equality in the maximum conflict? The maximum conflict tells us that the score has to be as different from the current classifier boundary as possible. So this is what previous works have proposed. The label equality says that we have to try to make sure that our labels are almost equal, near equal. Now, if we follow this active sampling strategy, we can get very fast, very high results compared to other active learning strategies. We have nearly 10% better performance for in the beginning. Okay, it's because of the zero shot prior, and in the end, it's around well, from 5 to 10% depending on the method. And this was tested both on HSUN and the small COCO dataset. Some interesting classes are the bicycle. So here we see that it's not just that the zero shot priors are better. Actually, that helps a lot. We're already in, near 0.1% average precision from the 0.29 in the end. So we start much faster because of our zero shot priors. Zero shot priors are very important. But even if we start from nearly the same type of accurate classifiers, we're still able to have much better final classification with our active learning strategy. BBAL is another method, which, a recent at the time framework for doing active learning. And here we see a plot of the convergence. We see that with the proposed active learning strategy, we can approach convergence between 0 and 500 samples. And in fact, actually, in some cases, you can have very, very good accuracy within the first few dozens of examples. Another way you can do interaction, so not just with the user, is like you have interaction with knowledge graphs for novel QI. So for image classification, so you can have the COCO detections, and then you can detect nodes in the knowledge graph. You propagate, and you expand the knowledge graph accordingly. So this work is, okay, ooh. Sorry, I'll lift the citation. That's the work from the More You Know, using knowledge graphs for image classification from our Marino et al. And then that's an example here how this works. So it discovers the tail, the trunk, and the mouse, and it goes over possible inferences from the knowledge graph. So the elephant has some connection to this type of attributes, but in the end, the network finds that the knowledge graph, the knowledge graph indicates that this is an elephant's shrew, given also the visual features that are available from the image. Another way you can interact with knowledge, external knowledge datasets, is for event detection. So for instance, let's say that you have some visual examples of how what fitting wall tiles look like in a video, or removing drywall, and then you want to find something new. You want to find out how what renovating home looks like. So that's again a zero-shot problem because you don't have any examples for renovating home. So what you are actually now looking for is a way to connect the novel query of renovating home with existing ones. And then perhaps say that since renovating home is, let's say, 30% of fitting wall tiles and 70% of removing drywall, make some sort of inference. This is work that was presented in this CVPR by a student of mine, titled Unified Embedding and Metric Learning for Zero Exemplary Event Detection. The model is composed of 3 parts. One is responsible for embedding the textual information. In the middle part, you got an event article, which embeds again the external knowledge from Wikipedia on the same space, and then the video is processed by a visual, like a convolutional neural network. The textual and the visual information are combined with a multitask loss, and the network is trained end-to-end. So like that, it's actually possible to connect event articles. So literally take information from Wikipedia, or WikiHow in this case, and connect it to particular videos that are available to you. For this work, we used the EventNet dataset, which creates links between WikiHow articles, which we consider external data source as the external data source, and the videos of respective events. As a conclusion, attributes are not always perfect, so often there is no good attribute definition for classes, and often attributes are not even that reliable. So knowledge transfer by external knowledge sources is a very relevant direction, quite interesting. It gets you ORALs in CVPR. And beyond that, you can actually do complex inferences about open world questions. In fact, I just read on Facebook there is a DRQA just released from James Weston for a model, a neural network model, that is able to answer open queries, open questions by retrieving information from Wikipedia. So you ask, for instance, how many countries exist in the world, and then the network is supposed to retrieve this type of information automatically by the most appropriate Wikipedia article, and then deliver the correct answer. So these are the type of open world questions that knowledge transfer via external knowledge sources can give you. It also makes inference, allows you to make inference beyond what static datasets can teach, and it allows for feature sharing via knowledge sharing. An interesting direction, in my opinion, is also active interaction for practical zero-shot classification. In practice, it's not going to be easy to trust a pure zero-shot model because it's never going to be as accurate as supervised classification. So in practice, if you want to have a product, you would like to somehow reuse old knowledge, which can be done by the zero-shot classifier, but also exploit the human intelligence. Such human intelligence can correct prediction mistakes through active learning and guide novel attribute learning and knowledge transfer. And quite importantly, in my opinion, by active transfer learning, you don't need to waste your old data sets. You can actually reuse them to have very, very fast convergence of your models. So that was it for me, for now. Do you have any questions? All right. So since there are no questions, I will conclude. I will make a summary, a wrap-up of what has been presented today in this workshop. This tutorial was about zero-shot learning, where, again, a recap is knowledge transfer from given a set of images and a set of existing training labels that we do know, transferring the knowledge to a new set of labels that we don't know, for which we don't have any visual examples. Namely, the training label set and the test label set are disjoint. The objective of zero-shot learning is to learn such a mapping function from X to Z via Y. Now, today we discussed about classification. Zeynep gave an excellent summary of zero-shot classification, also localization, retrieval by case, and we discussed some open problems, generalized zero-shot, for instance, interaction, active learning. And for zero-shot classification, mathematically ALE and DAP are similar, and ALE directly optimizes image classification. Zero-shot using pre-trained classifiers is a good way to go with indirect attribute prediction. There are several ways to do the knowledge transfer, the embeddings. You can use word-to-vec or coherence statistics, and we have a lot of models that do a form of one of the two. Those were presented by Zeynep, and it's very, very important to evaluate it. That's why now there is a benchmark. So do not try to fool yourselves. There are a lot of potential, but you have to be able to compare on fair grounds so that you make fair conclusions. For localization, the point that I tried to make, and I hope it resonates to you, is that attributes belong to objects, not images. So if I give you 20 attributes that characterize an image, that's the standard way classification is done. If I tell you mammal, brown, hairy, big, wings, as a composition of description, that doesn't make sense. You don't have such an object. You don't have such an image. But this can make sense if you assume that different objects exist in one image, in which case you want localization. You want to have a localization for just the mammal and the brown and hairy, and another localization, another bounding box for wings and beak and colorful for the parrot. So zero-shot localization is a natural extension to the problem. It's a more complex case than classification in terms of inference, because you have to detect something in the image, but it's also very rewarding because indeed, if you can actually localize something in the image by a zero-shot description, although you've never seen something like that, then you can be very, very certain that your zero-shot model has learned something. Now, you can focus either on visual details, so like floral patterns or like characteristics, visual patterns, or on big regions, and then try to summarize things. Each has their merit. And also localization in images and videos using natural language queries is possible and promising. Last year, there was natural language object retrieval by Berkeley, and this year we had the tracking by natural language specification from our group. I would highly recommend to read both papers. They're very, very interesting. Also, something that, a side note is that both offer a great evaluation framework for image captioning. Image captioning is another form of zero-shot because every new sentence is different. You cannot consider it as a fixed label. So image captioning is a sort of zero-shot learning, especially if you work in a question-answering task. And by grounding objects in images and videos allows for a very good pure computer vision way of evaluating things. Zero-shot retrieval tells us that it profits from semantic alignment, and it's learnable from freely available online sources. The next challenge is spatial temporal search and alerts for live video, and we saw some solutions from Cees on this. Open problems, as Zeynep described very acutely, the evaluation of zero-shot classifiers is very important, so don't forget, again, to evaluate. And thankfully, there is now a benchmark. This paper, provided by this paper, zero-shot learning, the good, bad, and the ugly, where 12 models are summarized and compared. Generalized zero-shot learning is a very interesting direction. It doesn't make sense to just expect that at test time you're going to have only unseen classes. In fact, for me, when I started working on this subject, I thought like I just didn't understand it correctly because I thought that would be like the way you should evaluate. But okay, it's obviously harder as we saw, and people were not doing that. Now people do that, and it makes more sense. Another open problem is how to optimally exploit knowledge graphs to answer novel questions. something that we saw is that interaction might be a remedy to attribute-based classification. How to do interaction is also an open problem. Active transfer learning offers a solution. All datasets are no more wasted, but I'm sure there are much better ways. So what's next? Well, there are lots of stuff. I think Zeynep had some papers on generating even images with text queries, or for having multiple cues for zero-shot learning. There's definitely a lot of things that can be done, especially with respect to the open problems. And, well, that was it. Sorry?